Welcome back. We are now going to have a talk from another Ben, and he's going to be talking on behalf of the Small Robot Company.
Hello everyone, my name is Ben Scott Robinson and I am co-founder and CEO of the Small Robot Company. And I feel like coming to present at Brez is a bit like coming home, because I think the first time I came into Brunel to talk robots was in 2018, when our company was very small and very conceptual. I think it was me and Joe, and that was half the company at the time had come along to see. So things have progressed a long way since then. We've worked with Brunel on a couple of projects. We have a Brunel PhD on board, and super keen to hopefully show you how we're getting on and inspire you into some of the stuff that we're doing. So, Small Robot Company. Well, I'd like to tell a little story, I suppose, about what Small Robot Company is, so you can understand that. But then I thought I'd want to tell you on a journey of one of our robots, which I first introduced to Ben and maybe some of you guys back in 2018, but has progressed quite a long way since then. So to show you that particular journey. So Small Robot Company started, Sam and I first started it because we came from different sides of the spectrum, but we both realized that farming was in trouble, particularly arable farming. So that is wheat and oats and barley and corn and stuff like that, the world's biggest crops, right? But the trouble with it is that there's a system that's been developed in the third agricultural revolution, which is been going now for about 100 years, one that uses tractors, one that essentially looks as farming as some sort of industrial process. And it's been very effective at increasing yields. So yields since the Second World War to now have quadrupled in size, gone from like 2 tons a hectare to 8 tons a hectare in the UK. But the trouble is that since the 90s, they've completely flatlined. They've completely stayed the same. But the machinery necessary to do this has doubled in value. The cost of people, the cost of seeds, cost of chemicals, all that sort of stuff has massively increased. So farming is completely unprofitable. And it means that a lot of farmers are completely reliant on subsidies. Obviously, those subsidies in the UK are going quite soon. So a lot of farmers are going, what do we do now? Our system doesn't work. Not only is it not profitable, to be able to try and drive out greater yields and stuff like that, farmers have been trying to get bigger machinery to make it more efficient, so drive that industrial process further and further. And actually what's happened is that that's just caused greater environmental destruction. So a big plow, a big farm, a big tractor pulling a big plow might weigh 40 tons, and it'll drag that plow through the soil down to a depth of about 3 or 4 feet. And by doing that, it completely rips up the soil and any sort of structure that's there. It releases a lot of carbon to the atmosphere, releases carbon dioxide. It also destroys and allows to be washed away all the lovely topsoil that's got all the nutrients in it, right? So it's not really not very good at all. And not only that, it is also means that when there are heavy rains, like there were here in autumn last year, when a farmer ploughs, all that lovely topsoil is literally washed away by the rain, and sometimes the seed with it. And because the vehicles are so big, the tractors are so big, if it rains too much, they can't get in the field. So what that means is, well, last year there was this tremendous sort of weather problem, and it meant that farmers couldn't plant. So 2/3 of farmers couldn't get their tractors and stuff out in the fields. Nearly half of them tried to plant later, but that didn't work. 3/4 of them suffered extra expenses, and we lost 40% of the winter wheat harvest last year. And that was just because of some rain. And that was the worst that it's been since the late 80s. So it just shows that the current system really isn't working. So we believe that this is a sign of something big, right? This isn't just a sign of something being able to change sort of machinery in some way to make it work. We believe that this is the end of the third agricultural revolution. The idea that you can have big heavyweight machinery that cultivates heavily, which means digs deeply into the soil to be able to turn it over, that when you look at one field, you can make a decision just based on that one field, and then just apply the chemicals or whatever it is off the top of that to make it work. We think that this is actually the start of something where a lot more precise, a lot more accurate, where you can start to understand, instead of an entire field, understand individual plants and just treat those individual plants. So massively reducing the amount of chemicals you need, but also using lightweight vehicles so you don't disturb the soil. So you don't need to plow heavily to be able to break up the compacted soil, which means that you can be much more sustainable and much more nutrient neutral. We believe this is the start of the fourth agricultural revolution. So the heart of what we're trying to achieve, more so than the robots themselves, is this idea of per plant farming, right? This idea that if you have accurate enough data where you can see individual plants in the field, and you can go back time and time again to collect that data over the course of the year, you can understand how that plant is growing, and you can understand exactly where that plant is. You can see every single crop plant in the field, but you can also see every single plant that's not a crop. And that, I don't mean weeds, because any plant that is in the field at the moment that is not a crop plant currently is viewed as a weed, but the vast majority of those plants aren't. So how can we allow for plants that are good and work next to crops really well to flourish and grow and support the crops growing, while taking out the plants that actually compete with the crops? So this is the heart of per plant farming, and we believe this is going to be so phenomenally successful that it will be the only way to grow crops by 2040. So how do we make this happen? Well, to do this, you can't just sort of replicate or automate one particular process. You have to look at the entire growing process to make it work. And you have to strip it back and redesign it from scratch. And most important, as far as farmers are concerned, you can't sell them robots because they don't have the cash. I told you at the start, they are running out of money. A lot of them rely on remortgaging their farms every year to be able to get by. So you have to provide it in a way which allows them to be able to adopt your technology without it having a big risk. So we provide farming as a service, where farmers pay per hectare, per year for our service, and that allows us to deliver a healthy crop at the end of the year. That means that we do everything. We do the monitoring of the crop and understanding how it's going. We do the processing of the data from the monitoring to be able to analyze it and create instructions. But we then also have the robots to go out and enact what happens off the back of those. So ultimately, we're doing the whole thing: planting, analysis, and treatment for all arable crops on a per hectare basis. So it's with great pleasure that I introduce you to the robots that are doing this. That's Tom, Dick, Harry, and the brains of the outfit, Wilma. So Tom's job is to live on the farm, completely autonomously, living in a kennel, going out all day, every day, and collecting information. 20 hectares a day, 200 hectares over 2 weeks. That allows us to be able to have this per plant continuous view of the crop as it grows. The information from Tom, 6 terabytes per robot per day, is then processed on the edge in the kennel, and then that processed data is then passed to Dick and Harry as instructions via Wilma. So this means that we can start to deliver this per plant farming model, which, as I say, massively reduces the amount of chemicals, reduces the damage to the land because we're not ploughing, we're leaving the soil alone, but also it can really increase yields. Now, we haven't got to the proof point here yet, but we know that there's a place, or there are places in the UK where per plant farming is already carried out. And that's in the research institutes where they look into how to grow or how to protect crops against disease. There they have these small plots of land which are essentially grown on a per plant basis. But instead of having a robot doing it, they've got people out with white coats and clipboards checking each individual plant. And they can get a yield of up to 20 tonnes per hectare. So if you remember, the average yield in the UK is 8.5 tonnes. The average yield in India is 1 tonne. This has the potential to have a massive difference worldwide. So I want to start by introducing you to the hardest worker, I suppose, of the robots we've got, and that's Tom. Now, this concept, this render that we show here, was the very first conceptual Tom that he came up with in 2017. And in many ways, it was the starting point for the whole process. So this Tom, the idea of a small robot, the orange, all the rest of it, was very much at the core of what we were trying to achieve. So what happened when we started trying to communicate what we were doing and encapsulate the ideas was that this became the point that people sort of gravitated towards. They looked at this and said, right, okay, we can understand that now. It's a small vehicle, it's going around, it's gathering the data, it's all very cool, and all the rest of it. And we got people very excited by it. And the first farmers who put money in was off the back of looking at this render, this particular picture. Now, obviously, the first task that Joe, our CTO, and Nemo, our first employee, who was actually an apprentice, came on board to try and achieve, was to make this Tom, to make this thing happen. And what we ended up with was this. You excuse me, there's a lot of names I'm going to throw around here, so bear with me. So this is Rachael. And Rachael was the first of our robots. And Rachael, I think, was the first robot that Ben met from us. Now, Rachael, in many ways, has a lot of the similarities, as you'll see, with the previous Tom. Using the sort of tail to be able to mount the GPS allowed us to be able to use a very low-cost RTK, so we could get locational accuracy to around about one centimetre. We used a phone on the back because the system of GPS that we were using was supposed to be for consumers and supposed to run in conjunction with an Android phone. Also, obviously, Android phones are fantastic pieces of computational power that allow us to do an awful lot. So very useful things to have on board. Just underneath the phone there at the back, you will see that there's a little bit sticking out, and that's where the camera is. And that downward-facing camera allowed us to collect our first data that we then fed through Wilma to be able to train our algorithms to be able to detect weeds and wheat growing up in a field. Now, Rachael is essentially a four-wheel drive skid steer robot. Very small motors, you can see there behind the wheels, and using a bogie system not dissimilar to the ones that you will see on, I know, the Mars rover and stuff like that. And quite a few robots use this. Starship robots, for example, use a six-wheel double bogie system like this. This is actually, the base of this is actually a kit that we bought from the US and was extremely useful to us. It was very, very rugged and really strong. And if you're looking to build wheeled robots, we strongly recommend that you use something like this as a starting point. Coming back to what this Rachael actually does, the key for this Rachael was to be able to go in a straight line, in a recordable fashion, to be able to take those images that I was taking using just a standard Raspberry Pi camera on the back and saving it into a Raspberry Pi on the device, pre-processing the data to give it a location stamp and a time stamp so that we know where it was, and really just be a platform for taking the images. And Rachael was really good at that. But the big problem with Rachael was that actually the amount of images that she needed, that she could take, were quite limited. So she only had a width, an operational width of about 1 meter. Now, we knew that we would have to try and cover 20 hectares a day to be able to achieve our operational goals. And when we applied that to the sort of the 1 meter width, it worked out that we would have to do about something like 30 to 35 miles an hour to be able to go through the field at the right pace. And for a little robot like Rachael, that's a hell of a lick and not really possible. So when we were looking at designing the more commercial elements of Rachael, we had to move to a slightly different scale. And there are a lot of people, I think, within the company who are a bit sad of that, because going back to the original concept, you know, so many people bought into this idea of a small robot going around collecting the data, something that was innocuous and safe. And so going bigger than Rachael was considered to be a little bit of an issue. Also, when you start scaling up the robots, as I'm sure you find when you start building stuff yourself, there are all sorts of issues that come in. You start to have customized components that need to be built for it. Buying stuff is a hell of a lot more expensive. You have to spend a lot more money and a lot more time before you get to the point where you can prove the point whether the robot works or not. So working with a small robot is really, really useful for that. And stepping up was definitely a challenge for us. So the first version of the robot was of the new robot was Super Tom. Now, Super Tom was entirely based around the boom. The whole point of it was to be able to give us a 6 meter wide coverage so we could collect enough data off those cameras. The little orange units on the boom are actually incredibly expensive super wide angle cameras to allow us to get the full 6 meter width. So this robot was, as I say, completely designed around that boom and being able to support the boom. You can see there's a huge amount of changes into the way that it works. If you look at the back unit, which is really the majority of the robot, you'll see that it's 4-wheel drive, 4-wheel steer. This was a huge step up for us, obviously, in terms of capability. Trying to design the steering system to work effectively alongside the 4-wheel drive was a real challenge. And also trying to make it as modular as possible. So in theory, you can swap out the legs and essentially just have one repeatable leg that you can just develop numbers all the way through. So this was a big challenge. We very also quickly realized that we really needed to have suspension. When the robot was moving, obviously you've got a lot of levers there, right? And there's a lot of movement at the end of those levers. So the cameras were really expensive, so they accounted for a lot of that with balancing on the cameras themselves. But even so, we had to try and even that out. So we built in a suspension system, which took a long time to get right, and arguably we never really got it right. Which is, you know, a bit disappointing. But having said that, I think it's also one of those things where you realize that if you're focused on the robot, you're not necessarily going to be an expert at off-road driving. So this was definitely a challenge. The other thing was that the weight was far greater than we expected it to be. We were hoping for Tom to come in at about 200 to 250 kilos. Super Tom ended up being closer to 400 kilos, despite the use of as what we thought was as lightweight possible aluminium in it. The processing power in it was much increased, so it's running NVIDIA Jetson boards to be able to control the unit, and obviously it's collecting a lot more data, so there was a separate board that was put in just to be able to process the data. But essentially it works in the same way as I was talking about with Rachael before. So this Super Tom allowed us, when it's working properly and in the right environment, to work at 1.5 meters per second, which is the correct speed that we needed to do, and in principle collect the 20 hectares of data a day that we needed. The trouble is that because of limitations with the design, limitations with the motive power, with the wheels, with the suspension, etc., various things, we were very rarely able to run it at that speed. But it was a fantastic thing to be able for us to look at and say what worked and what didn't, and allow us to move on. So the start of this year, January this year, we went back to the drawing board, quite literally, and said, okay, well, we need to work in this sort of way, but we need to develop something which is conceptually the same as this, but works, and really works at the sort of pace we were doing. And so that's when we came up with Super Tom V3. So Super Tom V3 has quite a few changes to the original. The first one, if we take the boom, rather than having a 3-meter boom with 2 very expensive cameras on it, we went for a 5-meter boom with 6 much cheaper cameras on it. This actually reduced the cost significantly because obviously even carbon fiber tubing, which is what we're using here, is substantially cheaper than the cameras that we were using. So to extend the boom made it much more reasonable. It also allowed us to put RTK GPSs on the end of the boom to give a much higher level of accuracy. So we now have a sub-centimeter accuracy with the location of the robot. A lot of work went into making sure that we could fold the boom up effectively, and that it sat within the envelope of the vehicle so that it could be transported in the back of a transit van without any issues. And the whole thing is designed so that we can get 2 of these in the back of a transit van, and that's a significant part of the design. Moving on to the chassis, rather than aluminium tubing, we found that by cutting from just pressed aluminium, we could get a much lighter chassis, and also using Fusion 360's FEA testing allowed us to be able to remove a vast majority of the material so we could get a really light, really strong chassis. It was absolutely fantastic. The next thing was looking at the suspension. So we actually outsourced this, and we went to a company called Randall, who are experts at developing off-road suspension, so much so that they work for Jaguar Land Rover, a number of racing teams and rally teams to be able to design their systems. And they found what we were talking about was a real challenge. But you will see, and if any of you know anything about very old cars, that what we have done is channeled the experience of a Citroen 2CV into making our robot work. And the reason for that is because the thing that the robot has to do is to provide a stable platform for the cameras, first and foremost. And by doing that, it was essentially replicating the brief for the Citroen 2CV, which was in 1947, I think, which was to carry a farmer and his wife across a ploughed field with a basket of eggs without breaking any of the eggs. Now, you know, in terms of closeness to our brief, there wasn't anything closer than that, so that was brilliant. We also benefited from bringing on board some of the Dyson electric car team. Now, they had just been let go in January, and some of them came on board almost immediately to help us out with a number of elements. One was the design of the chassis, and one was the design of the arm rotation units, or the leg rotation units. They were fantastic pieces of design, and to have that sort of skill set brought in was really, really strong for us. So that was the overall design. So let me take you through in a bit more detail. Oh, sorry. And then the next thing was, you know, we had to move to a situation where we looked more professional. So we wanted to move to developing a bodywork that would show how small and fine the Superton was, while also providing protection from the elements, some protection for people coming close, and also just a sense of a professional unit rather than what we were developing before. So I talked to you a bit about the chassis, but here you can really see how much it's been cut out. And I can't recommend enough that if you are designing something, that you spend the time to go through the FEA and you really strip out as much of the material as possible. You know, we lost somewhere between 2/3 and 3/4 of the original weight of the chassis by doing that. Which allowed us to then reduce the amount of the size of the motors that we needed, to change the suspension setup so they could be lighter, all sorts of things to make it a really strong unit. Now, I was speaking before about the sort of the leg units and the steering units. We specifically have these pieces cast. These are where the leg units go into the bottom of the chassis, and they're bonded to the chassis specifically. But we have these cast so that we could keep the weight to the absolute minimum. As you can see, the entire focus of this is around that radial point in the middle. And by bonding those in, they provide a nice, solid, strong environment for the robot. This scared a lot of people when we sort of showed this internally, because obviously there's a certain similarity to both the Spot, that slightly scary Boston Dynamics unit, and also the dog robot from Black Mirror as well. So luckily this sort of lost this look as soon as we put the wheels on it. But here I'd put this one in so you can see the suspension in place. Again, you can see if you look closely at the suspension, we've cut out all the weight we possibly can here to really, really bring the weight down. The shock absorber and springs are all set up specifically for the weight, and actually they had to change over time as the vehicle got lighter. And the motor is an unfortunate addition. We were really hoping to get a hub motor that we could put on here, but unfortunately trying to find a hub motor that works at the right torque and the right speed for us has been a bit of a challenge. But there you can see the suspension unit on. And here we have the sort of partially complete unit with the boom in place. As I say, it's the carbon fiber boom. It's super lightweight. I think it weighs in total 5 kilos. And the cameras and LEDs on it as well to allow us to get accurate photos for about another 2 or 3. It all folds up very neatly. It's also designed so that we can put servos into it so it can fold itself up when we get to full autonomy for the start of October 2021. It has a control, the robot itself has a control screen on the back, and it's all looking pretty neat. From a robotics perspective, just to give you an idea of the sort of the scale of and intricacy of the nervous system of the robot, we have this is the join between the sort of fully waterproof core, which is over on the right there, and all the input wires coming into that. So obviously there's an awful lot that's to do with the cameras, but an awful lot that's to do with the controls for the power for the wheels and the motors, the rotational motors, all this sort of stuff. So do not underestimate the importance of planning out and working through the schematics for how a robot works. We had this system laid out in the workshop for about a month. just like a nervous system, literally on a massive table, to make sure that we could get everything working and tied together properly. So here we go. So this is Superton V3. Superton V3 is now fully complete and just kicking off its trials. And just to refer you back to the original concept, you know, he's definitely much bigger, but is for what he is incredibly light. So 180 kilos rather than the 400 so kilos that we had for the Superton V1. Admittedly, little Rachael is significantly lighter than that, but because of the size of the wheels and the pressure that we run them at, the robot itself exerts less pressure on the ground than your foot does, which means it doesn't cause any compaction. It can also run over the top of crop plants without damaging them. The bodywork itself, as well as being inspired by quite a lot of 1980s sci-fi, is actually made from expanded polystyrene that's coated in epoxy. There's a fantastic company that's actually just down the road from us who cut polystyrene and coat it to achieve very light but still pretty sturdy stuff. By using this, it meant that we didn't have to create a frame inside the bodywork to be able to hold it in place. We could just have the bodywork cut to the right thickness. Also, by doing that, expanded polystyrene, when it hits people, sort of compacts and compresses. It's not hard. So it actually allows for a significant safety feature as well. So the other elements, I suppose, just to talk this through, is obviously safety. So the hard stops in all the corner and virtual stop is built into the control mechanism. But this robot, I think the key to it is completely integrated into our farming as a service system. This robot can be controlled remotely. It can be controlled by Wilma, the operating system, on its own. The data can be taken off and processed without anybody having anything to do with it. It is a completely autonomous unit. The only part of it which is not currently autonomous is the boom and its capacity to be able to put itself away in the kennel. But that is something that we're going to be working on. So there we go. So there's a little introduction to the evolution of a robot and how it goes from a concept all the way through to the reality and all the different parts of the journey that are in there. As you can see, the key thing when you're working on robotics like this is that you have to understand the environment you're trying to work in. You have to plan out in advance what you're going to do. And you have to set yourself clear requirements around things like weight, structure, and power and torque to make sure that you can design something that is effective and works. Starting from a design, starting from a concept can be risky, but it also gives you a guide and also allows you to understand the direction you should be going in. Now, we are, as a small robot company, growing. We are 35 people now. We're probably going to be about 50 by the end of this year. And we're probably going to be pushing 100 people by the end of next year. We've doubled year on year since we started, as Ben will be able to attest. And we are always keen to have a chat if you are looking to get into robotics and you want to save the world. So thank you very much for your time. I really appreciate it. I hope this was worthwhile. I know it was a bit geeky going into one thing, but hopefully I'm speaking to the right audience for that. Thank you very much.
Thank you so very much for that, Ben. So we're going to have a quick intermission before we go into our Q&A session. Hello and welcome back. We're very excited for this Q&A session on such an interesting and fascinating project. So the first question from the chat was, to what level do you collect the data from the crops?
To what level? Well, so we collect 20 hectares a day of imagery which is greater than life size, I think. So if you were to print out all the images that we're collecting, it will be bigger than the field that you collected it from. We are collecting it in RGB, so normal imagery. We're also collecting it in 3 very specific hyperspectral frequencies or spectra, so that we can detect very specific things. One of those is to detect slugs. So slugs have their own hyperspectral classifier using a hyperspectral frequency, so we can pick them out. And so that's like essentially 3 layers of images of the same data, hence it being 6 terabytes a day.
Wow, fascinating stuff. And on that sort of level, it's obviously you don't have all of the robots quite yet, but to what technology are you using or planning to use for that communication of all that data with all these robots?
Yep, that's a terrific question. So Tom is communicating at the moment with a mock-up kennel, I suppose you can say. So if you think about it, the kennel is a building which, you know, could look like the thing that Snoopy lives in. That's completely, you'd never get that reference. You know, but it's just a building ultimately that it goes into, a small building. But the key to the kennel is really the data transfer, the data processing, and the battery swap out. So what we have now is developed the data transfer and processing. So we're using it's an Ubuntu-based system, but just sort of running GPUs to be able to chunk through that data. We're actually working with a PhD from Brunel, looking at new ways of being able to process that data, so which is super cool. But ultimately, all that processing, the algorithm and the hardware, as integrated as they can possibly be, is on the edge in the kennel. Then the transfer of the process data, which is essentially a geospatial reference points and associated metadata, is then passed up to the cloud, where it goes into Rulma proper. And then we have a rules engine. I call it a rules engine. It's more sophisticated than that, but essentially that works through that to then determine the areas that need particular treatment, the particular plants in the field that need to be targeted, whether that's, you know, at the moment we're targeting weeds, but it could be crop plants that need spraying or whatever. And then off the back of that, then creating a route for the big robots to then go out and use. So it is, you know, that end-to-end experience thing has been completely linked together. In terms of technology that's using, again, that's using ROS modules and linking those together. So some of them we developed ourselves, some of them are inspired by existing open source ROS modules that are out there.
Fascinating stuff, fascinating stuff. That also actually kind of answers another question we had in the chat about kennel. So the next question I've got on the list is how fast can these robots take those pictures? Because obviously you're going quite fast, you've got quite a lot of cameras. What sort of, do you have a measurement of that speed?
That's a good question. I couldn't tell you off the top of my head. It is all synced with the pace that the robot's working, and with an understanding of coverage. So, you know, we have a sort of global understanding of the image coverage as we go along, so that we can make sure we're not leaving any gaps.
Yeah.
And that then triggers the next time the camera needs to take a photo, and that is obviously linked to how fast the robot's going. If the robot slightly skews out, you know, if it's thrown out by some mud or something, then it reacts to that and sort of takes photos so that it doesn't lose one part if there's a...
Oh, brilliant, yeah.
And then it also then dedupes the images, so it goes through and strips out the duped images so that we don't get a doubling up of data points.
You've really, really thought of everything and implemented everything. It's so brilliant. It's so fascinating to see such a progress from the start to the end of such a developed product. The next question was, instead of increasing the robot size, what considerations was taken into building multiple of the small robots, so Tom and Rachel? That was one of the questions from the chat.
And it's a very fair point. And that was really the choice that we had to make from the outset. And I think the thing for us was the restrictions around some hard physical costs. So from one side, the costs of, for example, the GPS units are one of the major costs of the device, and we would have to have GPS whatever we did. But there's no reason for us not to go back and redress that if we were, for example, to look at a mesh system that will allow us to do local localization and navigation. And in fact, with the weed killing system, we are going back to the drawing board and exploring whether we need a big robot like the Dick that you saw on there, or something that's much smaller, because actually with weed killing, we've got this interesting challenge that it comes in clumps, right?
Yeah.
So you don't have this sort of uniform requirement. So it might be that we have small robots that can go and kill the clumps that need to be killed, and can spread out more evenly. So it's an open question. For us, it was really based around cost initially, and us being able to meet that cost need, but there's no reason why we couldn't go back and redress that as we progress forward.
Brilliant. So that actually leads into my next question quite well. What's the idea for the scalability of this technology? Has there been any thought or planning into potentially having huge fields of 3 or 4 of each of these robots working in unison to cover ridiculous amounts of ground?
Yes. I mean, ultimately, I think that we have, we have to cover ridiculous amounts of ground because, our, 100,000 hectares is, 100,000 kilometers squared. Right? That's a lot of ground to cover. And that's what we need to do to break even. That's what we need to do to start making a profit. So for us to be able to achieve that, we have to have multiple robots. And as I mentioned before, the robots we designed, the starting criteria for us is the size of the back of a transit van. Because the people who take the robots out, they're not going to have a special driving license. They're going to be people who have come to us through an apprenticeship, because they're the ones who are looking after the robots and you're fixing them. They're not, sort of the ones who are doing all the fine development. So, and that cost is huge. Right, to have a person driving a van is actually more expensive over the course of a year than building the robots. So we need to be able to fit as many of the robots and as much capability and capacity into that as possible.
Oh, fascinating. As I keep saying, you've thought of everything. It's brilliant to see such implementation as thought. Obviously, you've got brilliant minds working with you and such dedication to what is an incredible project. My next question. My next question is, sorry, you've covered that one. You've covered so many of the questions in the presentation. There was a question in the chat asking, what were the issues with a drone-based approach?
That's a good question. So when we first started, as I say, we started actually by going out and speaking to farmers. And then we came up with the idea of the service, and then we came up with the idea of the robots. So when we first started, we thought, drones would be a really good way of doing it. But we found out a few problems. One is drones can't gather the granularity of data that we need. The imagery is not detailed enough for us to be able to do some of the things that we need to do. The second thing is that crop plants, when you're looking at disease, the disease starts on a crop plant, not at the top of the plant, but about halfway down where the leaves come out in the stem. Yeah? And that you have to be able to see that if you want to be able to target the disease before it's visible, because disease, which is usually fungal, so things like septoria, when they come out, when they grow in the plant, they grow inside the plant and they damage cells inside the plant. And then when they come to the surface and you see like browning or yellowing of the skin of the plant, that's when they're actually releasing spores so that they can go to other plants. So you need to catch the disease before it leaves the plant, which means that you need to have cameras that are underneath the foliage to be able to see that, and using a particular hyperspectral frequency to be able to look at the cellular damage. So which drones can't do. Drones can only see a disease spread when the whole plant is affected, and usually when a large area is affected, which is useless. Yeah. The final one is that soil. So we do a lot of analysis on the soil. In particular, we have a sensor which sniffs the soil to be able to detect the release of the different type of volatile organic compounds that bacteria give off to be able to tell whether the soil's healthy. So by sniffing the soil, we can see whether it's healthy or not, so we can understand how to treat that or what we need to do with it. Obviously, you can't do that from a drone, and you can't even see the soil once the plant has grown up to a certain height. So they're the 3 main reasons we do it. Sorry, that was a long-winded answer.
No, it's brilliant. That's fascinating, brilliant answer. Like, it's exactly the kind of thing we want from this kind of exposition. Unfortunately, that's all we really have time for. Thank you so very much for coming and speaking to us.